So thanks for the nice review, Scott, of what Lux is up to. And now we'll hear what their next experiment in their series of experiments is going to do. So feel free to take it away.
Yeah, thank you. So my name is Chami. I'm a grad student at Michigan, and I'm working on the LZ dark matter experiment. Like Scott mentioned, is a successor up and coming to Lux. So this work, particularly on anomaly finding in LZ, is some work that I've done with Scott and another collaborator, Maurice. So Scott set me up pretty well by talking about Lux. LZ is very much a lot of the same detection principles and a style of Lux. It's just a lot bigger. So this is an experiment that is in Leeds, South Dakota, where Lux was. And the detection principle is pretty much the same. So I'll just go over it super quickly what Scott mentioned before. You have a particle interaction with liquid xenon, potentially producing two signals. The first initial signal when it first hits a xenon atom is the S1 scintillation light. And this primary interaction also produces ionization electrons, which then drift up and are extracted into the gaseous xenon layer, which then scintillates, producing a secondary S2 signal. So here is an example of a waveform that one might see for an event. So if your primary S1 and some time later, and this time, as Scott mentioned, is a proxy for the depth of the interaction, you have a much larger S2. And oftentimes you have some after pulsing or various pulses following either S1 or S2. So this talk is about anomaly finding in LZ. So the goal here that we set out to do is to quickly identify and interpret anomalous data in high-dimensional spaces. So in other words, we are looking for a general purpose anomaly finder that has many uses that we will talk about very soon. So I mentioned high-dimensional spaces. Now, usually the usual analysis space that people work in these types of experiments is the S1 size versus the S2 size. So on the x-axis is S1 in units of photons detected. And on the y-axis is log base 10 of the size of the S2. The data shown in this plot, sorry, in the blue is tritium, which is a benchmark electron recoil calibration source. It emits an 18 keV beta particle, and it occupies this region of the signal space. And it's pretty clearly separable from the benchmark nuclear recoil spectrum. In this case, is a 40 GeV WIMP. And so these two are pretty separable in signal space, at least. But there are many more features that we can use in LZ's data in addition to S1 and S2. So some of these reduced quantities that we can think about using to pick out anomalous data are pulse, the shape of the pulse. So there are various RQs that can encode that are basically a summary of the shapes of the pulse, like the time it takes for the pulse to reach 10 or 5% or whatever percentage of the pulse area that Scott also mentioned before. We can include 3D position, the signal distributions in space. So basically, this pertains to which PMTs are firing and what are the areas that they detect. You can also put in RQs like the number of pulses in each event. So the waveform I showed in the earlier slide had a few events tagging after the S2. And using all of these RQs, we can put them in a general anomaly finder and identify things like rare backgrounds. It can serve as a tuning aid for simulations and data processing algorithms. This can also potentially speed up hand scanning, so just flipping through waveforms by human analyzers. And once we eventually have science data, we can put this in anomaly finders to find out unexpected detector anomalies that one might not expect. So in this vein, taking advantage of the high dimensional feature space that we have at our disposal, we've explored two unsupervised learning techniques for finding patterns in the simulated data so far. And these two are the isolation forest and the tSNE algorithm coupled with clustering. So I'm going to start talking about the isolation forest first. So the isolation forest is essentially an ensemble of random decision trees. And the way it works is you start at a root node, and you apply a uniformly random cut to a randomly chosen feature. And so you split into two branches, and you repeat these uniformly applied cuts to randomly chosen features recursively until you build a tree. And you stop when a data point is isolated from the other data points. And the main idea here is that outliers being few and far away from general populations take fewer cuts to isolate. So in this 2D example here, you can see this in action. You have your main distribution here, and you apply a series of cuts denoted by these red lines, and until you separate this XO point from the others. If you're trying to separate a point that's in the midst of the big population, you will need far more many more cuts than you would an outlier. So that's the basic principle. Using the length of the decision path, you can also calculate and define and calculate an anomaly score. And here is a distribution, a histogram of the anomaly score. You can set your anomaly threshold to be wherever you want and consider the points above that threshold anomalous. So isolation forests have a pretty cool feature that it's directly interpretable. So you can ask questions like, why is a certain event anomalous? What are the features that cause it to be anomalous, or why is a certain set of features collectively anomalous? And the way you do this is by looping through all the trees in your isolation forest and counting the features that are cut on the short decision trees. In other words, you're counting the features that are cut for the outliers. And so once you do that, you can make inferences like this. For example, in this plot, on the y-axis, you have a list of all the features that I fit into this into the isolation forest. And on the x-axis here, you have basically percentages of how many times they show up. So for this particular event, we can see that the pulse after the S2, so size, this means the size of the pulse after the S2 was particularly important in considering this event anomalous. And if you plot the distribution of the data in these two most important features, so the two most important are pulse after S2 size and the size of the S2 pulse after 200 nanoseconds. And you can see that this point is relatively well separated from the others, but these two are not the only features that contribute to the anomaly. It's, of course, a culmination of the other anomalous features. So the second method that we looked at is tSNE. So this is a t-distributed stochastic neighbor embedding, which is basically a dimensional reduction technique. And the main goal here is we have all these RQs or features. You can take about a set of 30 of them and visualize them in 2D space, which of course for humans is much easier to look at and discern clusters. And once you have this 2D compression of the data, you can use a clustering algorithm, in this case, something like DB scan, and look at why these clusters are formed. So the plot on the left shows the 30-dimensional feature space compressed down into two tSNE variables. You see a big population here and clusters orbiting it. We can translate this into the analysis space that is more familiar to us, S1 versus S2. And you can see that these clusters track pretty well to the clusters in S1, S2 space. Most of these clusters, we have a pretty good idea where they come from. For example, this red cluster at very low signal values, and this purple clusters at higher signal values. We, from other means, we know why these exist. But in this example, one puzzling thing is, why is this cyan population mixed in with the yellow? This is not something that is directly evident to us just by looking at S1, S2 space, just as we would if we didn't have, if we didn't do this. So this is one of the examples
just to let you know, you are getting close to time.
Okay, thanks. Examples of early successes is the cyan population turned out to be an inefficiency in one of our algorithms that we use to find pulses in the waveforms. All the cyan population data points turned out to have a long rise time, shown in this example waveform here. And yeah, after communicating this to the pulse finder folk, for example, they can implement a bug fix that removes this. The second example that shows the utility of a general purpose anomaly finder is rare background identification. So we can see in these plots, this is the usual S1 versus S2 plots. There are these backgrounds that we wish to cut out. In fact, these are the same backgrounds that Scott mentioned earlier, the gamma X, which come from incomplete ionization signals. And just by using a few features or RQs that are pertinent to this type of background, the isolation forest can pick out about 95% of these backgrounds, compared to truth data at a relatively low leakage rate. Okay, so unsupervised techniques, they're really useful, both to probe stuff that we already know about, but we want to find. Like, for example, we knew the gamma X background existed. We just wanted to pick them out. But also, they're useful in finding out the unknown unknowns. And an example of that was the long rise time case for the pulse. The isolation forest in particular is advantageous because it's interpretable. We know why certain events or groups of events are anomalous, and these allow us a better understanding of our data, which is always very important. Several applications I mentioned at the start include data quality, cutting out anomalous backgrounds, tuning algorithms in our data processing pipelines, and fixing simulation bugs. Okay, yeah, that's all I have, and thank you very much for listening.
Thanks.
All right.
Yeah, before we dive really into it, I just wanted to encourage people to put whatever questions. The meeting's only as good as the questions we get at the end. Let's repost that. But anyway, Seth.
So currently, the only question we have, why did you pick isolation forests and tSNEs in particular over, say, regular PCA, Gaussian mixtures, etc.?
Yeah, so we started this just maybe a few months ago, and of course we want to explore as many techniques as possible, and the techniques that we picked first were isolation forests, and we did some other work with local outlier factor techniques. But yeah, I guess we still haven't gotten to these. PCA, I would say, well, tSNE is I guess, a nonlinear PCA. So I guess it's more powerful in that sense. We definitely are, hoping to look into techniques like Gaussian mixtures. But yeah, there are a lot of techniques, and we can't cover all of them at once. But yeah, these are definitely on the radar.
Okay. We have another question now. Can Bayesian neural networks be used for anomaly finding?
Bayesian neural networks.
Bayesian neural networks.
I admit I don't know. I'm sure it could be, but I'm not qualified to answer that. Sorry.
Yeah, what are your priors on an anomaly?
Yeah.
Yeah, that's what I would want to know.
I'm used to hearing of Bayesian neural networks in the context of trying to understand better systematics and quantifying your uncertainties, but I'm not very familiar with it, so I don't know.
Yeah, maybe we should have gotten I'm not familiar either. Maybe we should have gotten a talk on that too.
Last question. Can you explain again how you get the two plots for tSNE?
Yeah. So briefly, to get the the left plot, you have your set of data that has about 30 features, and you put it through tSNE. And in tSNE, you can specify a number of things. There are some hyperparameters that you can tune, but importantly, you can specify your desired output, the dimensionality of your desired output space. And in this case, we've chosen 2, so we get a 2-dimensional representation of our data. To get from this plot to this plot, we've essentially just kept the colors and plotted the S1 versus S2. So yeah, this is how the clusters in tSNE space transform to clusters in S1, S2 space. And it's a pretty cool thing that the clusters in tSNE space, most of them at least, the red and the purple in particular, track to the clusters, to these clusters respectively in signal space. I hope that answered your question.
That seems to be all the questions we have.
Great. So now we have, what time is it? A 30-minute break. So people can have lunch, dinner, whatever. And then we're coming back to discussion room.